Great. Okay, we'll get started. Thank you for coming for the first of our PhD seminars of the summer term. So we're delighted today to actually, for our first ever invited external speaker, who's Gerardo from Queen Mary University. So Gerardo has worked with Matthias and some other people in the department, and you're going to be talking to us about generalized Bayes and Kalman filtering. So
yes,
without further ado, the floor is yours.
great, thank you. Thank you for the introduction and for the invitation. Today I'm going to be presenting the WOLF, which is our weighted likelihood filter. And this is joint work with Matthias and some other amazing people from UCL, Oxford, and Google DeepMind. But before I talk about weighted likelihood filters, I'm going to start talking about state space models, which we probably see in one way or the other. The type of state space model that I'm going to be focusing today are going to be these Gaussian state space models. And for anyone who hasn't seen a state space model, they have two main components, right? The first component is the state space, which is a latent process, something we don't see, but we assume that it evolves through time. And the measurement model, right, which is going to be this YT. So by this assumption, we assume that the state process is evolving in some way according to that function f of t, and some qt, which is going to be the dynamics. We don't really consider it noise, more as how much the actual process is moving through. So that's doing something, and we want to estimate that by considering measurements YT, which we're going to assume that it's also going to be normal with some measurement function ht. So usually what happens is that p is going to be of higher dimension than whatever we measure, right? And we want to estimate that state. And RT is going to be the measurement covariance, right? So how much noise is in the system. Now, there are a bunch of things we can do with an SSM, but the two things we're interested in this talk is either to estimate the state. That is, if I've observed a bunch of estimations from Y1 to YT, what's the estimate of theta t, right? So that's a typical assumption or problem. And the second one is the one step ahead forecast, right? So if I have observed sequence of data points from times 1 to time t minus 1, I want to make one step ahead forecast, right? And I want to basically forecast it just in one step. Now, why do we care about these sorts of problems? Well, the classical example is the tracking moving object problem, right? So we assume that you can take out your phone out, right? You're walking down the street, and then what your phone is actually sending to the cloud, right? So these noisy signals estimates, but that's not really your position, right? Your true position is going to be this gray line over here, right? So in this case, the true state, what is linear and unknown, is the actual position and the velocity at which you're moving, right? But you don't observe that. The only thing you observe is the x coordinate and the y coordinate, right? So the question is, well, how do I estimate this state space given that I only observe the measurements, right? So that's one example. The second example is weather forecasting. So this is simulation for a Lorentz 96 model, which is just a toy simulator, but basically tries to model the weather at any point in time, right? So it's like atmospheric pressures. And the idea here is that the state is this high dimensional state on the state of the atmosphere. And what we observe is the state of the atmosphere plus some noise, right? So in that case, the measurement function is going to be linear, right? It's just the identity. And we had a bunch of noise, right? And the idea is just to filter out the noise. What's the current state of the weather? Now, a more recent example, one that I personally like a lot, is that we can think of these problems as, the state can be anything. It doesn't need to have a physical interpretation. So we can, for instance, consider the parameters of a neural network as a state space, right? Something that, if the world is non-stationary, right, it's evolving through time, and if my only objective is to estimate the next prediction, then ideally, I want to find the parameters of the neural network that estimates the next observation that I have, right? So in this problem, what we have is a two hidden layer neural network. We measure these observations, and what I want is just to, make the next forecast. So the oracle here, the best possible prediction is this black line over here, and what I'm actually forecasting is this one over here, right? Now, this is a bit different to typical machine learning methods where we have a train set and a test set, right? In this case, the only test set is the next data point. And I want to predict that over and over. Great. So we have seen 3 examples. Now the question is, well, how do we estimate the state, right? How do we either estimate the parameters of the latent state, or how do we make a forecast? So if it turns out that the SSM is linear, right? It's Gaussian and linear, then the Kalman filter is the optimal filter in terms of residual mean squared error, right? Between the states, right? So if the only thing you care is the to minimize the RMSE between your true state and your estimated state. In terms of RMSE, the Kalman filter is the optimal filter. Now, that's a nice conclusion of the Kalman filter, but it also has closed form solutions, right? And if we're talking about neural networks, it would be nice to have something that is sequentially being updated, right? So computationally, it's also nice to have the Kalman filter. And it provides a framework to talk about the one step ahead for prediction, because it gives us this predict step, which is, well, what's the state of the world if I observe a bunch of data points, but I haven't observed the data point at time t? Or I can make an update, right? So first make a prediction, I check against my error, and then I make an update, right? Pretty straightforward. And the equations are pretty straightforward as well, right? In the prediction step, I'm just evolving the system one step according to this QT and the transition function ft for both the mean and the covariance. And the update step, I take whatever I predicted, and then I just make a comparison to get the new mean, right? So this is the mu at time t. It's going to be my predicted mean plus some common gain y minus y hat t, right? So it almost looks like the HGD update, right? Sort of thing. Just that instead of having a constant, now we have this gain matrix over here, right? So, okay, if the state space is linear and it's Gaussian, then the Kalman filter is the best thing we can do. But in reality, the world is not linear and it's not Gaussian, right? So there have been extensions to the Kalman filter that we can develop to tackle the nonlinearity problem, for example. The first one is the extended Kalman filter, and the second one is the ensemble Kalman filter. Now, just as a small caveat, there's a huge literature on how to tackle these non-Markovian, non-Gaussian, non-linear state space models. But for purposes of this talk, I've just focused on closed form update rules for computational tractability, right? I want to have something that has as close computational cost as the Kalman filter, right? That's my goal. So the first of those extensions is extended Kalman filter. And in this case, we assume that the state space is nonlinear, but it's Gaussian. And it's evolving according to this function ft and this function ht, right? But it's not linear. But suppose that it is differentiable, right? So one small tweak I can do is just compute the derivative for the first order approximation of f with respect to the previous mean, right? Which is something that I already know. And then the system, right? Even though it's non-linear originally, now I'm going to work in linear space. So I can just apply the Kalman filter pretty straightforward, right? We can see here that the state only depends on f linearly, right? It's going to be the state transition. And the vector space, the projection is also going to be linear, right? So I can make use of the equations that I saw before, and now I can just use extended Kalman filter. And that's nice, as long as the transition function here is not too nonlinear, right? It's just, it turns out that if ft is quite nonlinear, as in the weather forecasting model, right, which is evolving in a chaotic manner, then the extended Kalman filter is not the best thing we can do. So in that case, I can use the ensemble Kalman filter. And in this case, a particle-based method, but it still has closed form updates, right? I have a bunch of particles that evolve through time, but I want to make updates on those parameters and the distribution of the parameters as if they are Gaussian, right? Why? Well, just computational reasons, right? But there's really no theoretical reason why I would be doing this. Of course, unless f and h are linear, which are not going to be for the problems that we're interested in. Okay, so with these extensions and the Kalman filter, so the tracking problem, right, is usually tackled with the Kalman filter. That's the classical one. For the ensemble Kalman filter, right, for the weather forecasting problem, that's usually tackled using the ensemble Kalman filter, right? So it's highly nonlinear in the state space. And for the training of neural networks, like I I don't really know how to write a function for the transition of the states. So the best thing I can do is just say that it's linear, right? And then I can use the extended Kalman filter to train the neural network. But there's a problem with these methods, right? And it's that they're sensitive to outliers and misspecified measurement models. And what this means is that, for instance, in the tracking problem, right? If the errors that I see are not really Gaussian, but are, for instance, student T distributed, right? Then we can see that the estimate of the position, which is this is the Kalman filter, and the green line is the estimate of the Kalman filter, can be quite biased toward where the actual position is, right? So whereas we see noise, it's not noise, right? It's considered as if it were a signal, right? Which is not something correct. And this is due to the misspecified model, right? I'm assuming that it's going to be not heavy tail, but it is heavy tail. For the atmosphere model, suppose that for some, suppose that any component, right, we have this high dimensional vector that is evolving through time, and each of those components has probability of 0.2% of taking value of 100, right? So probably just one of the components is going to take value of 100. It's a big value, but it's just, one out of the 500 dimensional state. Then if you run the sample Kalman filter, right, things work well until they don't. And you're going to have these huge spikes over here where, we just see these massive signals over here, right? It takes a few steps to quickly revert back to the true state. And for the training of neural networks, well, I'm considering the Kalman filter. I don't really assume that the state space is Gaussian or the measurements are coming from the Gaussian distribution. But in this case, any measurement has a probability of 15% of taking value between -50 and 50, right? So clearly has no signal, and there's nothing I can do about it. So ideally, right, again, the forecast should be as close as possible to this black line, but that's not happening because it's being biased by these values that I observed.
I asked just
Yes, sir.
the neural network example. So do you assume the posterior is
Gaussian.
not Gaussian, but so do you assume it's like unimodal at least? So
Exactly.
kind of
Exactly.
do you assume
Yeah.
it's
Yeah.
unimodal?
It's unimodal at every time step, right?
Yeah.
So it could, for instance, be right here and then it jumps right here, right? But if it's that it is bimodal, then that's one of the drawbacks of the Kalman filter,
But
right?
you're not going to, because you can kind of have like local modes that kind of vanish.
Exactly. Yeah, you can imagine like then that it's bimodal, then it's going to predict the mean, right? It's going to be right in the middle. Just yeah. That's one of the drawbacks of these methods, but okay, so we have the Kalman filter, we have the ensemble Kalman filter, we have the extended Kalman filter, right? We said that we were going to use this just for computational tractability. The downsides is that they're not robust to outliers, right? So the next obvious question is, okay, how do we make it robust to outliers? And not surprisingly, there's a vast literature on how to make these models robust. And in recent years, variational base has been in vogue, right? And the idea here is, well, maybe the state space is just not the state as in theta and y, but also some other value, right? So, for instance, this method by Agamenoni and others, which is a compensation-based strategy, they assume that all of the observations that I have some noise, right? So if it's student T, this will work well, right? Because I'm assuming that it is heavy tail, I just don't know what's the measurement covariance at every time step T. Right, so now my state space is the state transition, which I already know, the measurement function, which I already know, and then have this prior on what's the measurement covariance, right? Which I am going to assume is a Wishart, inverse Wishart distribution, right? Now, if this is the case, then the posterior that I would like to compute is the one on the right. Right? What's this posterior distribution up here? And not surprisingly, it's not going to have a closed form solution, right? So what I can do is, let's consider the variational based posterior, right? So I consider the mean field variational inference. I just consider what's the closest distribution of these two that factorizes the product of R and a product of theta, right? And if you write this problem down and then you work out the math, and it's going to give you a brand new algorithm, right? But unfortunately, it's not going to be it's not going to have the same level of complexity as a Kalman filter, right? Because usually you have to do it multiple inner iterations. It's an implicit problem, so that's one of the drawbacks. So on the one hand, you have closed form-ish optics, But the downside is that now you have to pay a more computational cost. And you also rely on the fact that you hope that your assumption of what it means to be robust is well captured within this distribution over here. But imagine, okay, so this is one setting in which we can robustify the Kalman filter. But if the outliers bear no measurement, no information at all, right? As in where we have like this 15% probability of just taking noise values, then I can first assume that I can extend this state space to now include this random variable WT, right? And the point now is to have I extend the state space, and at every time step I want to decide whether the measurement that I have has some information or it doesn't have any information. If it does have information, I want to include it into my posterior computation, and if it doesn't, I just want to reject it, right? So again, I write down the SSM. It turns out that this has no closed form solution, but I'm hoping that the variational base posterior is going to have a iterative solution that I can just run over. And if it does, then I have a brand new algorithm, right? And of course, many methods have been invented out of this form, right? I can create a Durán-Martín 2024 that combines these two methods, right? In which we can take the methods, first check whether it has some information or not, and if it doesn't have any information, I can just make it conversation based. But that will make it, not surprisingly, not closed form, much computational higher, and reducing the purpose of these closed form solutions to have something as close to the Kalman filter as possible, right? In terms of computation, but this is just increasing the computation. Yes.
Sorry. Well, what's your definition of outlier? Is it not following that distribution?
For robust?
What's your definition of outliers?
We're going to show a definition in a little bit, but it's in terms of PIF, or posterior influence function.
Can you go back to the slide where you have the W?
This
How do you do you know whether a measurement is informative or not?
Wait, you want to compute the posterior of this? I mean, it's mostly based on, these models are really provably robust. The way these algorithms are introduced is just by intuition on that it might work, right? Which is, I agree with you, like it's a downside, right? It's not necessarily the case that it's going to capture some information, but by Bayesian intuition, you hope that they're going to capture. Does that make sense? Yeah. All right. But yeah, so going back to the robust Kalman filters by a variational base. The problem with these methods is that they're not straightforward to implement, right? So each new hierarchical method I introduce based on the nature of outlier is going to give a different new algorithm. They're not probably robust, which is based on that comment. I'm just hoping by Bayesian intuition that they're going to be robust, but there's not really something that is telling me that it's going to be robust in whatever sense I want to measure it from. And they're at least I times lower than the Kalman filter methods, right? Because it's going to be an implicit solution, never an exact closed form solution. Which takes me to our weighted likelihood filter of both. What we want to do here is we follow generalized space, and we say, well, if the model's going to be misspecified, I probably don't want to. I probably don't know the true measurements distribution, right? For instance, in neural networks, right? It's not true that the true measurement function is going to be a neural network, right? So under this perspective, I consider loss functions instead of likelihoods, right? So my generalized base posterior is going to be not the prior, it's going to be some generalized prior times the x of some loss function that I choose over here. And for reasons that we're going to see, the choice of loss function is going to take this form right here, right? So we observe it's simply going to be a weighted log likelihood of the observations, right? That's what we call it, the weighted observation likelihood filter. And the idea is that, okay, if this is the generalized base posterior, first of all, can we get closed form solutions? And second of all, is it provably robust? Right? So why do we choose this? Well, for some choice of WT, we show that our method is provably robust in a way that I'll show in a bit. It's straightforward to implement, and it's orders of magnitude faster than alternative robust methods. So whereas the Kalman filter is everything on black, our method is everything on red, right? So and surprisingly, that's all you need to make this methods robust, right? Which we see as an upside of our method, right? It's the simplicity and the probability robustness of this method. So again, if the state space model is linear, it takes this form. And now, well, the question is, which WT do I take? And there are a few that we consider in the paper, but in this case, we consider the IMQ weighting function, which simply downweights the observation in a polynomial manner rather than exponential. The way I like to think about it is that it measures our tolerance to the worst case scenario, right? Given by this hyperparameter C. So what's around the worst thing I would hope it happened, and then I can just set that to a C value. Now, okay, so we have a very straightforward to implement model. We see that W is really straightforward to implement, right? Simply a choice of observing how much far off my true prediction is from what I'm actually predicting. And then what do we mean by robustness? So we have this posterior influence function that computes two posterior distributions. One is the posterior distribution of the filter with observations from y all the way to time t. And at time t, I'm going to assume that some corrupted measurement happens. And then we're going to define a filter as robust if whatever the supremum of the absolute value of the PIF is bounded, right? So if I compute the supremum of this, if it's going to be less than infinity, then this is my definition of robustness. And as it turns out, we can prove that if the only requirements using the weighted likelihood filter to be robust is not in the posterior or the choice of measurement function, it's simply in the choice of weighting function, right? So as long as the weighting function is bounded in some first and second order conditions, then we can show that the filter is going to be robust in the PIF sense. And from this theorem, we can have some remarks. The first one is that, not surprisingly, the Kalman filter is not outlier robust. And the second one is that both our method with IMQ weighting function is outlier robust. Now, to show how this PIF looks like, we have this plot over here, which I quite like. And it basically measures the PIF. So this is for the 2D tracking problem, right? So we're tracking something, then an outlier happens, right? And this outlier is going to be centered at some value, and then we're going to move 5 units to the right, 5 units to the right, or 5 units to the left in each of the coordinates. And this plot here is showing how much influence this single observation is having on the posterior distribution that I compute. And what we see for the Kalman filter is that 5 units to the right already has a big influence, right? 60 units of PIF, it's a big number. Whereas the Wolf IMQ is bounded. This is a crop picture, but if you extend it over to around here, the maximum value takes around 6, and then it goes back, right? Another example is going to be this Wolf TMD, which is simply clipping value, right? One might say, well, the one thing you can say is just measure how many values you've observed, just take some quantile and then just clip whatever is outside that quantile, right? And it is robust in our definition, but the problem is that since you're tracking a moving object, right, you can have these weird pathologies over here where what you're actually predicting is not where it should be centered, so it can have high tails in the results. Right, okay, so we have our weighted likelihood filter, very straightforward to implement. Now let's see some examples. The first one is this, the 2D tracking problem. So first we have the Kalman filter, right, it's evolving through time. We saw that it was quite biased to the outliers, but our Wolf IMQ, as you can see, it's more or less tracks the true states more closely than the state space. Next is the atmosphere model. Basically, the Lorentz is small with the 5-dimensional states. And again, right, we have our weighted version of that is called AP, or average particle ensemble Kalman filter. And again, we see that it is robust to outliers in this sense. Right, so whenever an outlier is present, the ensemble Kalman filter is completely biased, and our method is not biased. And in sequential training of neural networks, we can also observe this exact same thing. Right, we're making measurements, we're making predictions, And we see that it's not quite biased to the measurements that are at the outliers. Great. And how does it compare to alternative methods? Well, we have this plot over here in which we do online learning of neural networks, right? So we have a data set, we corrupt it with some outliers, and then let's compare, I guess, the best thing we can do, right? Which is gradient descent. Right? We take a gradient descent, we take one data point, and we iterate that over and over. And we compute the error that we get divided by the error that we get for each of these methods minus 1, right? So the more left we are, and the more on the x-axis, and the more negative we are on the y-axis, is better, right? So we see that our method is as good as other proposed methods. This is the Agamenoni method that I showed, and this is the Wang method that I showed. So they have more or less the same performance, but they're orders of magnitude faster than the rest. And in terms of the Kalman filter, right, we get more or less the same computational cost. So this is Kalman filter, and this is the error, and this is our method, and this is how much error it has. Right. So yeah, well, there was just another slide over here, but the too long didn't watch of this talk is that we have a probably robust method. It's very straightforward to implement, and it's very extensible, right? Whereas these other methods focus on just one type of method, right? I either do the Kalman filter, or I do the ensemble Kalman filter, or I do unscented Kalman filter. Ours is a general framework to think about these filtering problems. Right. Thank you.
Thanks so much. Yeah, that was a great talk, and I think we've got plenty of time for questions. So, are there any questions in the room? Maybe I can start us off.
Yeah.
So, if we go back to the plot where you had the two errors on both axes.
Oh, this one.
Oh no, I think a couple before. It was in the tracking problem.
Oh, this one.
Yeah, so
Yeah.
a few before this, where you had the I think it was the PIF.
Oh, this one.
Yeah, so epsilon 1 and epsilon 2, these are your the noise in each direction.
Oh, yes.
So this is
So
right to think about.
yeah, so imagine they have this is 0.1, 0.2, 0.3. And then I'm just gonna take 0.3 and I'm gonna move it 5 units to the right, 5 units to the left. That's gonna be epsilon 1. And then it's going to be epsilon 2, right? 5 units above and 5 units down.
So you might have explained this, but so why do you get this asymmetry?
Oh yeah,
all
that's
methods compared to, because intuitively this feels like it should be a symmetric.
yeah.
There's no difference between going one way or the other, and you
Yeah.
could just flip the sign in your data.
Yeah. But what do you
So-
mean on the
For both the wolf methods.
this plot is the result of having this IMQ weighting function over here, which depends on your prediction, right? So I commit a decision of what's going to be my prediction at time t before I observe y(t) minus 1. So this will be center. Hopefully this makes sense. If yt is the exact same as yt without the errors,
Okay.
right? So imagine there are no outliers.
Yeah.
Right? Then in the best scenario, yt hat is going to be yt. So that's going to be 0. And then imagine that I move it 5 units to the left and 5 units to the right. Then that's going to be symmetric. But since it's a tracking problem, I first make a prediction, and then this is not going to be centered. So even the best estimate of what could happen is not perfect. Does that make sense?
Okay, so this isn't like an analytic thing. This is like these are
Exactly.
empirical plots.
Exactly. Yeah. Exactly. Yeah, this is an empirical plot on the 2D tracking plot, right? Just simulate one path. And then ideally you would like to predict yt without any outliers, right? Imagine that you know anything about the model, about the world, but you don't really know what's going to be the next measurement. So I committed a decision, and that's going to be the best thing I can do is something that you don't know. And after that, you get the outliers. So that's why it is symmetric plots up here, right? Because ideally you would like to predict around here.
Yeah.
And this would be like yt0, but you already made a decision at yt minus 1.
I see.
Does that make
Yeah,
sense?
yeah, I see.
Yeah.
Yes. Any other questions in the room? Yeah. Laurie.
Yes.
Why did you choose the specific WT?
Well, we have a few. One is the thresholded one, and we show that has heavy tails. If you use exponential, as far as I know, they decays quite quickly. What you say is an outlier, right? So you end up saying that everything is an outlier. And this, more or less, if you look at it from a probabilistic perspective, looks like a Cauchy distribution, right? So it's like, yeah. Not a student, it would be like a student T with 2 degrees of freedom, right? Yeah, so it's robust in this sense. Yeah. I know there are other interpretations, but yeah, this is the one that I like.
Any other questions? Don't know if we have anything.
There's nothing.
I had one more then maybe.
Yes.
So you said with the alternative methods, so assume you build some hierarchical Bayesian model.
Yeah.
You say these are not provably robust.
Yes.
Are they provably not robust?
No, I mean, they're
So
they
do
just
you kind of,
constructed.
okay, do
You
you kind of
can-
know how this
Exactly,
behaves?
exactly. I mean, by construction, they're not provably robust, but it might be the case that using our framework, right, we can analyze what's the PIF.
Okay.
But they don't say, okay, let's consider some measurement of what it means to be robust. And then let's construct this hierarchical model, and then let's show that it is robust.
Okay.
So
but-
they just, yeah, they just
So-
say, I think it's gonna be robust.
So they don't do this, but is there anyone who has some idea like
Well-
how the PIF for these guys behaves?
It's going to be robust. Well, empirically can tell you that they're going to be robust as long as the type of outlier they have is the one that you assume is going to have, right?
Okay.
For example, for this one, if you really have these sort of outliers where, really has no information.
Yeah.
Then this is just gonna shine, right? Because it really has no information. But if for some reason you assume that, not really, every data point that I have has information, then it's gonna.
Okay, yeah.
This is the one. So,
Yeah, so if you know you have a contamination model, then
Exactly,
Okay.
exactly. If you have some prior if you have a prior on the nature of outliers, then, in that sense, you can
Yeah.
more or less argue that it's going to be robust.
Okay.
Yeah.
Okay, last chance for any questions? Okay, then I think we can thank the speaker one more time.
Right.
And we'll be back next week. In case you didn't have enough generalized Bayes this week, we'll have more generalized Bayes next week, because it's Matthias's turn. So Matthias will be speaking to us, I think same time next week. So hopefully see you then. Well, thank you very much. Thank you again.
Thank you.